So, cybersecurity for SCAI. Cybersecurity for industrial control in general has become a topic of increasing urgency over the last decade. So those of us who aren't in information security roles, say we're in automation or functional safety, there are certain concepts, certain topics, certain terminology we need to know about because it is going to, at an increasing level, interact with what we do for a living. So I'm going to cover some key terms and concepts. I'm going to provide a very, very brief overview of some key standards related to cybersecurity for industrial control systems, and SCAI in particular. We're going to discuss briefly how cybersecurity for SCAI is different than cybersecurity for your standard IT system. Think about your office network. I'm going to share with you a handful of SCAI or industrial control network architectures, which include both the safety and the process control functionality. And we can look together about how those different architectures are going to impact the ease or difficulty of implementing cybersecurity countermeasures for those systems. And then there'll be some closing remarks. So to begin with terminology, most of you are familiar with a number of these acronyms and abbreviations, but the ones I've highlighted in blue are the ones you're going to see in the diagrams over and over again. HMI, human machine interface, the operator workstation, how the operators interact with the automated system. IACS, industrial automation and control system. Some of the standards shortened that to ICS, just saying industrial control system. IT, information technology, again, envision your standard office computer network server environment. SCAI, safety, controls, alarms, and interlocks. Those are the instrumented protections that we use in process hazard analysis for risk reduction. SIS, safety instrumented systems, is a subset of SCAI. And in trying to explain what the IX is versus what IT is, a picture's worth 1,000 words. This is a diagram from the upcoming draft of the Guidelines for Safe Automation book. And it starts up here, level 4 of the network, which is the enterprise network. Otherwise, again, think your office computers, the servers, the printers, everything that makes the computers in your office environment work. Your IX system is down here, levels 2 through 0. The process control network, the process control and safety controllers themselves, and the field instrumentation. Pretty much everything that should be needed for reliable control and functional safety should be somewhere in levels 2 through 0. So what about this level 3, this process information network? That's colloquially referred to as a demilitarized zone. You install a PIN, a process information network, within the overall network so that you have a place for information to be pushed to from your control systems so that the enterprise network has a place to pull information from without directly exposing your control systems to the level of cyber risk that exists at the enterprise network. That's the primary purpose of the PIN. Here's where the SCAI is. Again, it's the components necessary to execute safety controls, alarms, and interlocks. That's why the safety HMI is included in this bound of SCAI, because without the safety HMI, you don't have safety alarms. So some of the key standards that relate to cybersecurity for industrial control systems. I'm going to start on the left, the ones we're familiar with for functional safety, IEC 61508 and IEC 61511 or ISA 84, the U.S. adoption. What do they say about cybersecurity? Well, before 2010, and these standards were published in mid to late 90s, they didn't say anything. But in 2010, IEC 61508, the provision that came out that fall, included the requirement that safety requirement specification for the SIS had to include how that we were going to address cybersecurity for that safety instrument system. That change is rippling down into the new revision of 61511, which should publish later this year, maybe early next year. which will then roll into the US adoption ISA 84. So these are the standards that say you need to do something about cybersecurity for your safety instrument systems. But what do you need to do? Well, that's where IEC 62443 comes in. That's a suite of 13 documents. It used to be ISA 99. And indeed, some of the content is still being transitioned over to the new number and the new document format, but it addresses cybersecurity for industrial control. That's 15 documents in total. That's why we have TR 8409. TR, Technical Report, is a guidance document put together to merge material from all of these normative documents into one guideline that will help us implement cybersecurity for safety instrument systems and the related control systems. And I'd like to give a shout out to NIST 882. That's the Guide to Industrial Control System Security, put out by the National Institute of Standards and Technology. Now, one thing I like about NIST is it does a really good comparison between cyber for information technology and cyber for industrial control. And they are not the same. There's a fairly long table in this comparing these two. I'm only going to hit a handful of topics. First is the concern to the defender, the owner of the system. If you're doing IT defense, what's the priorities? Accessibility. If your clients can't get to your website to order your product, you don't sell anything. If your computer system in your offices go down, you're so dependent nowadays on our computers, the productivity of your employees pretty much goes to nil. Very closely, data confidentiality. All intellectual property, and indeed also HIPAA information that exists within the enterprise network needs to be protected against unauthorized access. Discussing IT defense. From a cyber attack, a very distant third priority is data integrity. Usually those teams don't think about someone reaching in not to steal something, not to shut down your system, but to change something secretly, get out. That is the very first thing that we're worried about when we're trying to do cybersecurity for an industrial control system. Someone reaching into our controllers and making them behave in a way that they're not supposed to. Very closely is accessibility, so for that we're similar. But for industrial control cybersecurity, data confidentiality is a far, far distant third place. Usually the data that's inside our industrial control systems is raw data. Raw pressure and temperature readings, flow readings. It's not the digested information that an attacker would find readily usable and sellable out on the market. So we usually don't worry about that quite as much. Similarly, what's the likely objective of an intentional attacker? For an IT system, they're coming in to attack your enterprise network. They're usually there for one of two reasons. Stealing information or shutting your system down, causing business disruption. They're trying to cost you money or get money for themselves. An intentional attacker for an industrial control system has a very different likely objective. They are most likely there to cause harm, damage to your assets, harm to your personnel, harm to the environment, damage to your reputation and license to operate. Very, very different consequence if a cyber attack succeeds against an industrial control system. How much skill does it take to attack? Well, sad to say, but it takes virtually no skill today to launch an attack against an undefended enterprise network. Why? Because the necessary tools and tutorials are publicly available. There's YouTubes out there if you really wanted to learn how to go attack a normal IT system. What about industrial control systems? It depends. If you'd asked this question a decade ago, there was the belief that we had security through obscurity, that the proprietary languages and technologies used by industrial control were such that it would make it prohibitively expensive, if not impossible, for a cyber attack to succeed at getting through. And the SCAI systems are physically separate from the process control systems, aren't they? Well, these past beliefs do not jive with current realities. The current realities are that more and more the industrial control systems are using commercial, off-the-shelf hardware and software technologies. More and more they're being intentionally designed to network easily. Why? Because we, the end user clients, ask them to. Because we want to have seamless access to our information from our mobile devices halfway around the world. Training on the common controller systems, things like Siemens, for example, and training on the malware is, again, widely accessible through the internet. So there really isn't a specialized skill that's necessary to launch an attack. And cyber attacks are now big business. There are organizations that launch cyber attacks to whom the cost of doing so is no barrier at all. So all of these differences result in differences also in the countermeasures and the recovery from an attack. Think about your computer in your office. How often do you see a security patch come through? And you're encouraged, yes, you need to load those, and how often with those patches come maybe an unexpected result in one of your applications you use for your work? Don't worry, in a couple hours they'll figure it out and they'll send out a new patch. Okay? That's not going to work in an industrial control system. The countermeasures for cybersecurity cannot jeopardize the ability to control the facility safely. Control must go on. Think back to your office. If patching didn't work, you think you've maybe been subject to attack, one of the first things that you're going to do is reboot the computer. Try to interrupt that cyber attack, which it usually does. Not an option for an industrial control system, at least not while the plant's running. And then finally, if rebooting doesn't work, you're going to reload from your last clean backup. Get back in business, get back working. You can't simply reload damaged equipment and injured personnel. Again, that fundamental difference in consequence changes the likelihood of a recovery of a successful cyber attack in any sort of short period of time. So is this real, or am I just flooding you? Okay. I can't tell you how far back the first successful cyber attack in a control system was, but starting in 2001, I found no shortage of headlines of confirmed successful attacks against industrial control systems. Almost everyone's heard about Stuxnet, but that was by no means the first nor the last. So in short, yes, this is real. Now, good news is we have standards that give us life cycles and tools to help us address cybersecurity for an industrial control system. We're starting with the work process. You see I have the safety life cycle up here next to the IX cybersecurity work process. Why? Because you're going to find the work processes are essentially identical. It makes sense because this is all about risk management. So safety, we start with a risk assessment. We develop a conceptual protection strategy. Hopefully we pause to do a preliminary design review. We go into our detailed design of our safety controls, alarms, and interlocks. Hopefully our project has a detailed design review. We implement, verify, and validate. There's our mandatory review for our pre-startup safety review. And then we're into operate, maintain, auditing, and change management. And depending on what we change, we go somewhere back up in the life cycle. The work process for developing industrial control cybersecurity is the same. And we agree there's information that should be leveraged back and forth between these parallel processes. So, for example, these cybersecurity risk assessments take inputs from the process hazard analysis and conceptual protection strategy design. We then do a conceptual countermeasure design that has information to feed back to preliminary design reviews. Detailed countermeasure design has information that feeds back to detailed design reviews. We implement, verify, and validate the countermeasures. Well, that should definitely feed back into the pre-startup safety review. And then to operate, maintain, auditing, and change management. Here's where the similarities end. Talking first about the change management cycle. How do the hazards of your process change? Fundamentally, not that often. The safety life cycle has a slower change cycle, and accordingly, it has a slower audit cycle, typically somewhere in the range maybe 3 to 5 years. Cybersecurity protections, on the other hand, have a very rapid change cycle, and it takes a rapid audit cycle to keep up with the management systems and make sure they're working the way that you expect them to. And part of the reason why this is cyber protection is a moving target. Our safety functions, their effectiveness degrade due to entropy and neglect. There's well-known causes for this, and there's well-known solutions, whether or not everyone implements those solutions robustly. For cybersecurity, the degradation comes from active attack. Black hats, the bad guys out there, are actively inventing new attack mechanisms constantly. And the manufacturers of our industrial control system components are constantly creating new technologies, easier to use, easier to network. They're creating new vulnerabilities daily. Okay, that's part of why there's such a rapid cycle for the cybersecurity work process, as opposed to the safety life cycle. So what does a cybersecurity risk target look like? Think about your process hazard analysis. You're usually looking for impacts on safety, environment, assets. Some people split out the financial cost separate from physical damage, okay? So you might have a safety 3, an environmental 2, an asset 4. There are 7 foundational requirements for industrial control cybersecurity. So identification and authentication. Can you identify every user, whether it's a human, a process, a program, that tries to gain access to the system? Once you know who they are, can you apply use control? Can you restrict their activities to what they're authorized to do? System integrity. Again, how good is the system at protecting against someone coming in and making unauthorized changes? Data confidentiality. How good is the system at protecting against theft of information? Restricted data flow. In these large networks, there is communications that should take place. But are you watching for communications that aren't supposed to be taking place? And are you restricting that ability? Timely response to events. How good is the system going to be at detecting an attack and responding and giving you a chance to recover? And then finally, resource availability. What this particular item means is how good is the system at avoiding or defending against denial of service attacks, an attack that comes in with the intention to overwhelm the system and shut down your capability. For each of these 7 foundational requirements, there can be a level from 0 to 4. 0, we're not worried about it. No cybersecurity protections needed. 1, okay, we need to protect against coincidental or casual impact. Level 2 starts the intentional attacks. We have something we're worried about here. We need to defend against intentional attack. It's someone using low skills, low motivation, low level of resources. Level 3 goes up to moderate skills, moderate motivation. And again, more and more this IX specific skills is becoming not an issue either way. Level 4, sophisticated means extended resources, high motivation. What's the example of a security level 4? State-funded cyber terrorism, corporate-funded cyber terrorism, large crime syndicate funded cyber terrorism. Basically, they have really deep pockets, and they're willing to take their time. So a cybersecurity target vector will normally take the form of something like this. It's a vector of 7 numbers. So we've got a target we're shooting for. How do we design countermeasures against those targets? We need to know a few things first. 1, where are the likely threat sources for our system? When we think threat sources for cybersecurity, we all think the malicious hacker. That black hat, that bad guy out there in the internet is trying to reach in. We also need to consider authorized third-party contractors. If we are outsourcing the support of our controllers, those people have to have access somehow, and if we've given them remote access, we've now created a potential threat source. Not necessarily malicious, But if they upload a new version to the controller, what happens if the controller then needs to reboot? And you're running. Okay? That's not going to be a happy situation. Well-meaning insider. What do we mean by that? That's a person going about their everyday job, trying to do what you're paying them to do, just in a way that happens to violate your security standards and maybe open your system up to an attack. Then there's the malicious insider, intentional sabotage. It is very difficult to defend against intentional sabotage of an industrial control system. You know, frankly, if you've got your computers well locked down, you can take a pair of channel locks and go out and start impacting tubing in the field. Some attacks can involve a combination of sources. So a well-meaning insider, taking their USB stick, which they're not supposed to plug in their computer, they plug it in anyway, and it just so happens it's infected by malicious code written by a malicious hacker. The other thing you need to know is where those attacks could come from. So not just the source, but what channel are they going to take? And again, everyone thinks about these connections up here to the internet at the enterprise network, making it all the way through the controller. We also need to think about the industrial control component manufacturers. Okay, again, two ways. They could be upgrading devices to make it easier to connect, creating new cyber vulnerabilities that didn't exist. Or it could be that the manufacturer facility has been contaminated, infected with malicious code, and you get a device brand new out of the package that already has virus. Remote access, like we talked about before. If you give third-party contractor remote access support, maybe it's even your engineers remote access support, you've now created a channel behind one or more of your cybersecurity defenses. Some people even have remote access support jacked directly into their safety controllers. And not many controllers today that are implemented in the installed base have a whole lot of host-based cyber defenses. Consider that before you go down that route. Obviously, you're giving machine interfaces in your engineering workstations. If someone could just walk up to the computer that's supposed to give instructions to the controller and start typing stuff in, you may or may not like the results. Mobile devices and mobile code. Pretty much everything from level 1 on up will have a jack of some sort. USB, Ethernet, serial, something. Someone could connect something to that might then upload malicious code. With smart instruments, more and more, you have that capability at the field instrument level, where the maintenance personnel walk around with their little communicators, plug in, you check the settings, so on and so forth. Is this clean? Have you practiced good cybersecurity hygiene on that field device? So we now have that list there. Similarly, wireless field devices. And by wireless, I do not just mean radio, it could be satellite, anything that's not hardwired to the controller that's using it. With that technology, I don't even have to plug something into it to infect the system. I can beam a signal, man in the middle, swooping signal, and start making the controllers think that things are going on in the field that actually don't match reality. So, countermeasures. So we know where our threats are coming from, we know who they could be from. What are we going to do about it? I cannot emphasize enough physical security control. Your gates, guards, and guns level of your security play a very big role in cybersecurity as well. But then there's a host of cybersecurity countermeasures. Password protections, authentication, intrusion detection, your firewalls, your network switch settings, all seems like a whole lot we could do, right? Well, for industrial control systems, there's two basic problems. Some of these countermeasures, the control systems, again, in the installed base today, don't have a lot of that capability. They're not bad ideas, they're indeed maybe very good ideas. We just can't do them because the technology won't support them. Then there are countermeasures that can be problematic for an industrial control. Cryptography, smart card authentication, virus detection. One of two things, why this cause prone. It'll either introduce latency, delays in the control system response, which may mean your control system's now no longer fast enough for your process, doesn't work anymore. or it may interfere with an operator or an engineer in an emergency situation, making a correct and necessary interaction with the controller, because there's been some hiccup in the authentication. So those can be problematic. And when deciding what the countermeasure design is going to be, this is where the network architecture is huge, and it really does matter. How they're connected will significantly change the effectiveness of countermeasures. In the following examples, all of the SCAI safety functions, including safety alarms, are being executed by the controllers that are in the safety network zone. Again, safety network zone, we're talking safety engineering workstation, safety controllers in this case, instruments, and the safety HMI. All of those components are necessary to execute safety controls, alarms, and interlocks. So first architecture, probably the easiest one, air-gapped. You show it displayed as two zones, control and safety. What are these network zones I'm talking about? The contents of each zone have a different set of cybersecurity principles. So for example, the type of interaction that's typically allowed between the operator and the controller on the process control side isn't always allowed interaction for the safety controllers. So you need two cybersecurity zones there. And it's actually possible with this architecture. Notice what's not there. Open space I circled. In an air-gapped architecture, there's no permanent digital connection between the SCAI and remote change support. It's still not immune to cybersecurity attacks, though. You still have to guard the safety controller against mobile devices and physical interaction. Let's take the architecture one notch different. We still have two zones. This is an interface system. Now, we have a digital connection between the two controllers, but it's COM to COM, a point-to-point communication between the computers themselves. Okay? This is creating a vector for a limited number of cybersecurity attacks. I say limited because the COM to COM links are normally in very restricted protocols supported by the embedded software of the controller hardware. Usually those links cannot transmit malicious code. But you could have an attack that tries to overwhelm this link, basically make the controller just spam messages out to that SCAI system. So the firewall should be there to defend against that. The loss of the communication, if the SCAI has been set up correctly, it should still do its job whether or not it's getting the signal from the process controller. So we're just trying to keep from overwhelming the COM and possibly slowing down the controller to where it's, again, too slow to operate the process. What's different about this one? Picture kind of looks the same, right? Still two zones. We still have a digital connection, but notice where the digital connection is. Between the network switches. You can transmit a lot of information that way, but it's being transmitted over commercial off-the-shelf network technology. Okay, that's your standard IT network switch technology. Now, your SCAI controller, everything here in the safety zone is vulnerable to the broad range of cybersecurity threats that could come at you. Denial of service, man in the middle. They could mock the output to your safety HMI. So while they're wrecking the plant, the operators can't see it. Things stuff snapped. Strong controls are needed at that firewall and those network switches to defend. Because again, the SCAI controller itself and the devices attached to the switch don't have a whole lot of host-based cybersecurity options open. Finally, down to one zone. This still has two controllers, process control and the SCAI object solver. But we're sharing a network switch. And in this particular architecture, we're also sharing an remote I/O bus. Why is it one zone? I still have two controllers. I still have a firewall. No, it's one zone because I can no longer sever this connection from the SCAI controller and retain all of my SCAI functionality. If I sever this connection here, I no longer have safety alarms. That's why everything in here needs to be managed to a SCAI level of cybersecurity. It's a one-zone architecture now. Often the controllers in this kind of architecture are using the same controller technology. So if the cyber tech gets through that network switch, it is very likely to impact both of those controllers in the same way. And the shared I/O creates additional vulnerabilities. Again, man-in-the-middle or spoofing attacks could get information in here. That is what the SCAI is using to create the safety controls, alarms, and interlocks. Okay. So hopefully I've given everyone the impression convenient access and ease of security are diametrically opposed concepts. You cannot decrease one without increasing the other. I'm going to talk for a moment about SCADA. SCADA brings a whole new level of cyber threat into the picture. Why? Because the IX, the control functionality, is actually spread up into IT space. You've got this computer center that's doing the production scheduling down to these site-wide production controls that are coordinating the activities of all of these units. So part of the control is now being done typically over public networks. There's not a whole lot of companies that have the resources to install their own personal, private, dedicated network through all of their physical facilities. Instrumentation for SCADA-based systems uses wireless more frequently, with, again, the host of cybersecurity threats that brings to the picture. So my personal recommendation when looking at a SCADA system, strongly consider using local, hardwired, non-programmable technologies for your most critical safety controls, alarms, and interlocks. Because there's a whole lot of attack vectors in a system like this. Again, some of them are over public networks, which we know are just teeming with malware. So it'd be nice to have something in the system to protect you at least from a safety event or an environmental event that's not subject to those vulnerabilities. Taking a moment to step back to TR 8409. Again, that's that guideline document that pulls together the requirements from the normative documents. So we have one place we go to get guidance on cybersecurity for safety incident systems. Those documents go through a cycle themselves. Right now, TR 8409 team is in the process of expanding the content to talk about cyber for associated IX, or the rest of SCAI, not just SIS. We're adding more detail to the work steps in the process, restructuring the existing content to transparently align with the work process so it's easier for the reader to follow along. And those comparisons that I did of those different architectures, there's even more architectures involved and expanded comparisons that talk about the difference at each of those 7 foundational requirements that's going to be implemented in the next version of TR 8409. So in summary, don't connect what you don't have to connect. Is convenient access to your SCAI worth the risk? If you are going to connect it, be prepared to actively defend it. Disable unused features and guard all the approaches that remain. And don't just wait for the incident to happen and then have the investigation afterwards. Proactively monitor access through those gateways and firewalls, because often an industrial control cyber attack begins with a series of smaller attacks as the attacking organization is getting the information they need to put together a very effective punch all the way through to the control system. You have a chance to be forewarned. Respect the differences between IT and industrial control cybersecurity. You need adequate resources of both. Your process automation and functional safety people are not going to be experts in IT cybersecurity technology. And your standard IT security professional may not be familiar with the nuances of cybersecurity for industrial control systems. So they need to work carefully together. And your end users, you need to train them, you need to train them, you need to drill them, you need to audit them. Because ultimately, you have vulnerabilities at the human level of social engineering. When the attacker gets stopped by your automatic controls, he says, maybe if I call this guy up, I can convince him to turn it off for me. You'd be surprised, that type of attack often works. You need your personnel to be prepared to reject that type of attack. So there are the list of references.